Welcome to the second lesson of my Thermodynamics course. In this lesson, we will first be going over the definition of a thermodynamic property. So, as intuitively as this may sound, a property is simply a characteristic of a system. So, for example, this could be either pressure, temperature, or volume. Since each of these, of course, generally describe the condition of a system. And now do note that we have two different types of properties, one of which are intensive properties. And these are properties that are simply independent of a system's mass. A few examples of these can be temperature, pressure, and density. And now you may be wondering how exactly density is considered an intensive property when it is typically related to mass, since density by definition is mass per unit volume. But the reason why it's an intensive property is because density is simply a ratio of mass and volume, which practically remains constant no matter the size or amount of the substance. So always be sure to keep that in mind. And a good way to remember what intensive properties are is to notice that the word intensive starts with the letters IN, and so does the word independent. So now the second types of properties are extensive properties, which are basically the opposite of intensive properties, as these are properties which values depend on the size of a system. So for example, this can be the total mass or total volume of a system. So there you have the two major types of properties in thermodynamics. And now to help further demonstrate intensive and extensive properties, I'll go ahead and draw a sketch here as referenced in the book. So this square practically represents a system which is made up of mass, volume, temperature, pressure, and density. And now if we were to evenly divide this system in two, just like so, then we would notice that our two extensive properties, mass and volume, will be divided in half because these properties are again dependent on the size of the system. So the two properties on top are of course our extensive properties, mass and volume. And then the unaffected properties down below are unaffected by the change in the system because they are independent of the mass of the system. So these are the intensive properties in the system. And so a key takeaway is that each part of the split system will have the same value of intensive properties as the original system, but half the value of extensive properties. And now a subcategory of properties are specific properties, and these are simply extensive properties per unit mass. So for example, a specific property is a measurement known as specific volume, denoted by lowercase v, which is simply volume per unit mass, capital V divided by m. And another one is specific total energy, lowercase e, which is total energy per unit mass, capital E over m. So again, note that these are all properties per unit mass. In other words, properties divided by mass. And also notice that these are typically denoted by lowercase letters. So moving on, we now cover the concept of a continuum, which partly forms the basis of the study of thermodynamics and fluid mechanics. And so, what exactly is a continuum, you might ask? Well, simply put, a continuum refers to continuous and homogeneous matter that has no holes or gaps throughout. And now a few key points to remember for a continuum are first that a continuum calls for properties to be treated as point functions. Next, we must assume that properties vary continually in space without any jump discontinuities. And lastly, any idealization is valid as long as the size of a system is large enough relative to the space between molecules. So again, that's a major point that should be repeated. Idealization is valid as long as the size of a system is large relative to the space between molecules. So of course this might be quite a mouthful, but I'll go ahead and dive further into this by drawing out a quick sketch here to help visualize this. So say we have a glass container that is filled with water. Of course, chemically this water is made up of very small molecules of H2O, which of course are each one oxygen atom bonded to two hydrogen atoms. And as a liquid, of course, there's going to be some distance between these molecules, which I'll simply denote as S. But because these molecules are so small, the distance between them is known to be much smaller than the overall size of the glass. And so because of this, we can use the idealization that the density of water is generally equal at all points in the container. So this right here is the derived idealization based on the concept of a continuum for this example. So again, because the space between the molecules is much smaller than the size of the glass, the overall system, this idealization is valid. So hopefully this helps you further understand the concept of continuum. But of course, we're going to keep looking at more examples and practice problems later on to help you further grasp this concept. And now one last thing to add to this is that gases can generally be treated as a continuum, partly due to the very large number of molecules that are present in a gas. So yes, we can definitely come up with idealizations for gases, just as we did for the liquid. And also keep in mind that this is despite the large gaps between these molecules. And now the next thing we should cover here is, of course, density. Density again is defined as mass per unit volume, which in other words simply means mass divided by volume. So density rho equals mass m divided by unit volume v. And so the SI units are typically kilograms per cubic meters. So remember, mass m per unit volume v. Moving on, we also have another property, which is specific volume. And specific volume, again, is simply volume per unit mass. So this is where we have lowercase v equals capital V over m. And also notice here that this is basically the inverse of density. So this is equivalent to 1 over rho. And now do note that for liquids and solids, the variation of density with pressure is usually negligible in most practices. So density variation with pressure, negligible. And also density more greatly depends on temperature overall. So in most thermodynamic practices, temperature will have a bigger effect on density. Just like specific volume, we also have specific gravity, which is also known as relative density. And so specific gravity is the ratio of the density of a substance to the density of a standard substance, for example, water, that is at a specific temperature. And now this standard substance is usually water at 4 degrees Celsius with a density of 1,000 kilograms per cubic meter. So ratio of density of substance to density of standard substance at specific temperature. And so the formula for this will typically look like Sg is equal to rho over rho H2O. And so this is basically a unitless measurement. So that is specific gravity or relative density. Moving on, we also have specific weight. And specific weight is basically the weight of the unit volume of a substance. And the formula for this is gamma sub s equals rho times g, where rho again is the density and g is the acceleration due to gravity. And the SI units are newtons per cubic meter. And of course, we get these units since density is in kilograms per cubic meter, while acceleration due to gravity is meters per second squared. So multiplying these units together, we have kilograms times meters over cubic meters times seconds squared. And now recall that this portion right here, kilogram meters over second squared, is essentially newtons. So that is how we end up with newtons per cubic meters. And of course, remember that newtons are equivalent to kilogram meters per second squared, since this is basically multiplying mass, kilograms, times acceleration, meters per second squared, which is, of course, equivalent to force in newtons. Next, we'll go ahead and define a state. So a state is simply a condition of a system that does not undergo any change, including properties across the system. So again, a system's condition that does not undergo change, including the system's properties. Additionally, we must fundamentally assume that there are no unbalanced forces within a system that is under equilibrium. And note that equilibrium here is similar to static equilibrium, where the summation of forces equals 0. So there are no unbalanced forces within a system under equilibrium. Next, we must also assume that a system under equilibrium ultimately experiences no change when it is isolated from its surroundings. So systems under equilibrium experience no change when isolated from surroundings. So now a form of equilibrium which we must understand is thermoequilibrium. And this is essentially a state where temperature is the same throughout a system. In other words, there is no more temperature difference. So hopefully this is an intuitive definition to understand. And now just to give a quick visual example of thermoequilibrium, again, we're going to revisit the coffee mug example, where we have a cup of hot coffee that is left on a table in a room that is at room temperature. And of course, if you recall, heat moves from hot to cold, so heat will transfer from the hot coffee to the colder air in the room, and hence the coffee will lose energy to that air and consequently cool down. So for instance, let's just say that the hot coffee is initially at 180 degrees Fahrenheit in state 1, and the cold air is at 75 degrees Fahrenheit. For thermal equilibrium to be achieved, of course, in state 2, the temperature of the coffee has to be equal to that of the surrounding. So ideally, the coffee will cool down to a temperature of 75 degrees Fahrenheit, being equal to that of the surrounding. So this is essentially what thermoequilibrium looks like, where there is no more transfer of heat between two mediums. Now similarly, we also have the concept of mechanical equilibrium, which involves pressure rather than heat. As for this type of equilibrium, there is fundamentally no change in pressure or force at any point of a system over time. So again, no changes in pressure or force at any point of a system over time. So essentially, delta P equals 0. Additionally, here we must also note that any pressure variation that results from gravity is relatively small and oftentimes negligible. So pressure variation resulting by gravity is relatively small and negligible in most thermodynamic systems. So for instance, any pressure related to any difference in potential or height will oftentimes be negligible, as this is of course related to gravity. Next up, we also have phase equilibrium, which is pretty much whenever the mass of each phase in a system involving two phases reaches an equilibrium level and remains. So the mass of each phase in a system that involves two phases reaches and maintains an equilibrium level. Additionally, there is also chemical equilibrium. And simply put, this is whenever a system's chemical composition does not change with time. So there are basically no chemical reactions that occur over time. Next, there is also the principle of state postulate, which basically entails that the state of a simple compressible system is completely specified by two independent intensive properties. And the state postulate also defines the number of properties that are required to fix the state of a system, or in other words, the number of properties needed to describe a system in thermoequilibrium. And now you may be wondering what exactly describes a simple compressible system. Well, essentially, this is a system that has no electrical, magnetic, gravitational, motion, and surface tension effects. So it does not experience any of these external forces. And here we assume that effects are due to external forces and are often negligible. So effects that arise from external forces are negligible. And now the state of a simple compressible system can be described by two independent intensive properties, which is again based on the state postulate. And it is also worth noting that two properties are independent if one property can vary while the other is kept constant. And now, for example, temperature and specific volume are both independent properties, which as a result can together fix the state of a simple compressible system.